All right, on to 7.1b. So now we're looking at the volume created by revolving an area. So we take an area and we're going to spin it around one of the axes or some other line somewhere. All right, so here's the idea. So we have an area either between like some function, say y equals f of x, or between a function and a line, between a function and an axis or something. And we're going to take this area, which we can find just doing the integral. Like this is just the integral from a to b of f of x dx, right? Because each of these little rectangles is a dx wide, and each one has a height of r, which is the same thing as our function f of x here. Right? So now if we take that area and we spin it around the axis, so each one of these little, I guess instead of making a little rectangle, we'll now be making a bunch of little cylinders. And each cylinder will have a width of our delta x, and it'll be like the volume of a cylinder, which is pi r squared times the height, where the height is our delta x, and our r will be the radius from the axis, or from wherever we're spinning around, up to the edge. All right, and that edge will often just be like our function f of x. And then we'll, don't forget to have the pi out there, and we'll integrate that from a to b again. So that brings us basically, so this is me going through those formulas. So there's our volume formula. There it is with our delta x and our radius, and that's each delta v, each little section of volume. And then if we add up all those, we do a summation of all those, as n goes to infinity, we end up getting this as our volume formula. It's basically pi r squared, right? Because each one's kind of a circle with a tiny little dx width. All right, now we can also go up and down the y-axis instead. So if we go up and down the y-axis, our radius will no longer be a function of x, but will now be a function of y, and will be, our little delta y's will be counting up the y-axis, so we'll be integrating dy. So here are those little delta x's, and they were counting down the x-axis in each direction, and this height was a function of x. So we either need to have everything in terms of x or everything in terms of y. And don't forget the pi outside. All right, so here's our first example. Find the volume of the region formed by revolving the region bounded by the graph of f of x equals sine of x, square root of sine of x, and the x-axis. So in other words, between 0 and pi, about the x-axis. So we're taking this little area here. So this is the graph of f of x equals the square root of sine of x. The black line here is the graph. And we're going to take this and we're going to revolve it around the x-axis. So we're going to take this and just spin it around and just keep spinning it and spinning it and spinning it until it looks like this, kind of like a football almost, maybe more like a rugby ball. All right, but this will be just a nice round ball here. And it will have some sort of a radius, which will be the height straight up. So our radius is the height here from the x-axis up to the curve. Well, the height from the x-axis up to the curve is y. All right, it's just the letter y. In this case, our y is measured by sine of x. All right, so this is our radius function in terms of x. And then our dx's are going down the x-axis. So that means we're going to start at 0 and go to pi. So the volume of that area is going to be, and don't forget the pi out front, pi times the integral from 0 to pi of our function. Our radius function is the square root of sine of x, quantity squared, dx. So if now it's just a matter of solving this integral. So the square root of sine squared is just going to give us sine. Actually, it's absolute value of sine, but it doesn't particularly matter because it's already going to be positive. So we just get sine of x dx. And now we're going to integrate sine. And the integral of sine is cosine. I always forget, is the integral of sine cosine, or is it negative sine, or negative cosine? I think it's negative cosine. There we go. From 0 to pi. And now we plug in pi. I'm just going to leave this pi out front. So we get negative cosine of pi minus negative cosine of 0. All right, so negative cosine of pi is negative 1. So that will change to that. And this is 1. So that will change to plus. So we'll have 1 plus 1 in here times the pi out front, and we get 2 pi. So the area of this section as we roll it around here or spin it around the x-axis is just 2 pi. All right, let's try another one here. So find the volume of the solid form by revolving the region bounded by f of x equals 2 minus x squared and g equals 1 about the line y equals 1. So if we're revolving it around this line, so here's the graph. So here's our f of x. This is our parabola opening down, 2 minus x squared. And then here's the line g equals 1, or I guess g of x equals 1 or y equals 1. And that's what we're going to revolve around. So we're spinning around that line. So we're taking this area here and spinning it around until it makes this sort of shape. This kind of rounded shape. So I should do dotted lines around the back here. And it's going to have this radius here, which is going to be the height here. But that height is the difference between f of x and g of x. So my radius is going to be f of x minus g of x. All right, and in this case, my radius f of x is 2 minus x squared minus g of x, which is 1. All right, and we're going to have all that squared. And we're going to go from -1 to 1 while we make these little rectangles, or what will be cylinders, right? Circular cylinders as we spin them around. So the volume here will be pi times the integral from -1 to 1 of, let's see, this here, 2 minus 1 is 1, so 1 minus x squared. 1 minus x squared is our radius, quantity squared dx. All right, so we can work that out if we want. If we also notice that it's symmetric, we could go actually from 0 to 1 and then just double it. That would also work. All right, but either way, we're going to have to square this out. We can't really do substitution here. So if we square this out, we get pi times the integral from -1 to 1 of 1 minus 2x squared plus x to the 4th dx. Just foiling this out. So now we integrate. And we get pi times x minus 2x cubed over 3 plus x to the 5th over 5 from -1 to 1. This is where it might have been easier to change it to 2 times the interval from 0 to 1, but it's fine. We can do this. So we get pi times, plug in 1, we get 1 minus 2/3 plus 1/5 minus, now plug in -1. -1. We're going to have minus -2/3, so that'll be plus 2/3, and then minus 1/5. All right, so we can distribute the negative here, so that's going to change that to plus, minus, plus. So we get 1 minus 2/3 plus 1/5 plus 1 minus 2/3 plus 1/5. So 1 and 1 is 2, 1/5 and 1/5 is 2/5. And we've got minus 2/3 and minus 2/3 more, so that's minus 4/3. From here, it's just a matter of, do we want to get a common denominator and combine like terms or not? You can if you want to. I'm going to save it for later. All right, but I do want to say that we could actually also find the volume of the region revolved around the x-axis. So what if instead of revolving around this line, we revolved around down here? Let's see if I can erase some stuff here. All right, so what if instead of revolving around there, we revolved around here? And then what we get is kind of like this shape down here, and it would be kind of an empty middle section, and it would be spinning around. All right, so that's coming up in a later section. But now instead of making discs, we have open discs, or what we call washers with open middles. So this is coming next. So this is coming in 7.2. All right, but I just wanted to give you a preview while we were here. All right, next one, revolving around the y-axis. So those were all around x-axis or y equals something. So those were all revolving this direction. Now we're going to be revolving that way, around the y-axis. So these were all around x-axis type things. So we want to rotate y equals x squared and the y-axis from 1 to 3. So let's take a look at the graph. So first up, here is y equals x squared. And we want to revolve that around the y-axis. Here's our y-axis. So we're going around this guy from 1 to 3. So from 1 all the way up to 3. So basically we're taking this region and spinning it around here. All right, so we're taking this and spinning it around, and we're going to get this kind of, it's kind of almost like a bowl, but kind of missing the bottom of the bowl. All right, so from the axis out to the curve, that's going to be our radius. And we want our radius in terms of y, because our little dx's, like we're going to make a bunch of little rectangles here, and our delta x's are actually delta y's. So we want our radius as some function of y. All right, but the question is, what is it? Well, if we're going straight from the axis out to some curve, this is really just an x value. Right? That distance over is just an x value. All right, and the x value we're using is what we would solve for here. So if we solve this for x, that's what we get. So if we solve this, we get x equals the square root of y. Technically it's plus or minus, but the minus would be over on this side over here. The plus would be on this side. This is the one we're working with. So we get that. All right. So now we can say, okay, so our volume must be pi times the integral from, we were going from 1 to 3, of our radius, which is that, square root of y, squared, dy. And if we can just square that out, we get pi times the integral from 1 to 3 of y dy. So if we integrate that, we get pi times y squared over 2 from 1 to 3. So we get pi times 9/2 minus 1/2, which is 8/2, or 4. So we get 4 pi. Now, if that seemed strange to you or weird to you, you can switch everything. All right, so we could switch everything. We could say x equals y squared, and we're going from x equals 1 to x equals 3, and we're going around the x-axis. And you can try and do it that way. All right, so if we solve this, we'd get y equals the square root of x, and it would look fairly similar, right? Square root of x is going to look like that. We're going from 1 to 3. And we're just spinning that around this axis here. All right, and it's making this sort of shape here. Here's our radius. And we're going to have a bunch of dx's or delta x's going down the x-axis because we're spinning around that. And the volume here would be pi times the integral from 1 to 3. Here our height is actually just a y value because it's going from the x-axis up to the curve. And our y value is just the square root of x. So this would be the square root of x dx. And if you notice, oops, I forgot the squared, r squared. It's the same integral as this, it just has the different variable. So if you want to switch all your variables, if that's what's throwing you out, switch all the variables. It's okay. That works. It does the same thing. It'll get you the same answer. All right, so that's my revolving for volumes. We will have some more volume methods later, but this is it for 7.1. All right, so go get that homework done.